Hello students, welcome to JP's Academy and I am Nitin sir. In today's session students, in the next 15 minutes we will try and cover all the topics in the chapter Atomic Structure. So before we jump into the lecture, I request you all to please subscribe to the channel, like the video and share your comments. Let's start students. The first topic students that we're going to start with is the discovery of subatomic particles, starting with the discovery of the electrons. Students, the discovery of the electrons started with the cathode ray tube experiment, where there was a discharge tube, and in the discharge tube students we had a gas at a very low pressure and very high voltage was applied, and what was observed is that behind the anode subatomic particle electrons were discovered. This experiment was done by Thomson. Now students, what was observed in the experiment is that the nature of the cathode rays or cathode particle is independent of the gas which was taken in the discharge tube. Second students, what was observed is that he calculated a very important parameter which is called as the charge to mass ratio, and the charge to mass ratio students is 1.75 into 10 raised to 11 coulomb per kg. I've also written some other properties. Now students, using this parameter of charge to mass ratio and Millikan's oil drop experiment, the charge on the electron was calculated, and the charge on the electron is around negative 1.6 into 10 raised to minus 19 coulombs. Students, this is also taken as unit negative charge. Also, the mass of the electron is around 9.1 into 10 raised to minus 31 kgs. All these points are important from students from a numerical perspective. Next topic that we have after this is the discovery of protons. You will see students that the setup looks very similar, that we have a discharge tube, we have a gas inside the discharge tube, which is at low pressure, a high voltage was applied. However students, this time the particles were discovered behind the cathode. Now students, 2 points that we need to remember over here is, when we talk about cathode rays originate from cathode, but anode rays do not originate from the anode, they originate somewhere in between. Second point that students we need to remember over here is, unlike cathode rays, positively charged particles, which is anode rays, which was later discovered, is here the nature, or protons depend upon the nature of the gas. So when you change the gas, the charge to mass ratio would change. That was not the case in electrons. Second, the cathode rays originate from cathode, anode rays do not originate from the anode. Then the charge on proton was calculated, which is 1.6 into 10 raised to minus 19 coulomb. The mass of the proton was calculated, which is around 1.673 into 10 raised to minus 27 kgs. Another point here students, this mass of proton is around 1837, or approximately 1840 times the mass of the electron. So the charge density on the electron is very large. In a small size there is more charge, and the charge of the proton students is also called as unit positive charge. The next topic students we have is the discovery of neutrons. So neutrons are neutral particles. James Chadwick was doing an experiment where alpha particles are doubly ionized helium ions. Alpha particles were bombarded on beryllium, and what was observed that a chargeless particle was discovered. This chargeless particle student is neutron. Neutron has no charge, but students, what we need to remember here is that the mass of neutron is 1.675 into 10 raised to minus 27 kgs, almost the same as mass of the proton. Moving ahead, next we have students different atomic terms. For example, atomic number, it is the number of protons. In a neutral atom, it is also equal to the number of electrons. Second, we have atomic mass number students. Atomic mass number is the number of nucleons. which is the number of protons plus the number of electrons. Students, I have not mentioned atomic number and atomic mass number, but I have mentioned some other important atomic terms, starting with isotope. Isotope, same atomic number. Isobar, same atomic mass number. Isotones or isoneutrons or isoneutronic species are same number of neutrons. Next we have isoelectronic, which is same number of electrons. I have also given the examples. Students, you can pause the video, copy this. You can also make this as your own short notes for the chapter. Next we have, students, isosters. Isosters are same number of atoms and same number of electrons. Next we have isodiffers. Isodiffers are the same difference in the number of neutrons and protons. I've given some examples over here. I have left some space over here so that, students, you can write the examples and you can then eventually solve these. The next topic, students, that we have is different atomic model. Now, students, after Thomson's experiment, what J.J. Thomson did is he gave an atomic model. The Thomson's atomic model is also called as plum pudding model or watermelon model. Because Thomson discovered the electrons, so the protons or nucleus was not yet discovered. So in Thomson's atomic model, what we have is that an atom is a sphere, and the positive charge is uniformly distributed through the atom, and negative charge are like electrons which are embedded. Now, students, this model could not explain spectra or could not explain certain points which were placed. However, this was the first atomic model. The model could actually explain the neutrality of the atom, but spectra and many other points could not be explained by Thomson's model. And the next, before we directly jump onto the next atomic model, we have a small experiment which is called as Rutherford's gold foil experiment. So let's understand what was Rutherford's gold foil experiment. In Rutherford's gold foil experiment, a very thin foil, okay, students, very thin foil was bombarded with alpha particles. Now, what was observed is that majority of the alpha particles went straight through. Okay, majority of the alpha particles went straight through. This tells us that almost everything in the atom is empty. You can say that 99.99% of the atom is empty. Few particles deflected through a small angle, and very few particles, students, 1 in 20,000 particles deflected by a greater angle. Now, students, this led to the conclusion that majority mass of the atom is concentrated at the center, which was later called as the nucleus. Now, along with that, what Rutherford's gold foil experiment also gave us is something called as the distance of closest approach. Now, students, this was used to actually even find the size of the atom. So if you look at the size of the nucleus, it is somewhere around 10 raised to minus 15 meters, and the size of the atom is around 10 raised to minus 10 meters. Now, what is the distance of closest approach, students? If I look at the alpha particle which had a head-on collision with the nucleus rebounded back. The entire kinetic energy which would have been present here, as the alpha particle slowed down, this got converted into potential energy, and then there was a rebound. So the initial kinetic energy of the alpha particle would be equal to the potential energy, and using this, the distance r of the closest approach was calculated, and here we have the formula which you can use to find r. However, students, there are many drawbacks of Rutherford's model. Let's consider one drawback. According to Maxwell's electromagnetic theory, whenever a charged particle moves around another charged particle, there is loss of energy. So eventually what should happen is the electron should spiral inward into the nucleus. However, this couldn't be explained by Rutherford as to why the atom is so stable, and hence we have to move on to the next model, which will be Bohr's model. But before we jump onto Bohr's model, let's consider the wave nature. Let's study the wave nature and the particle nature of light. Now, let's start with the wave nature of light. James Maxwell also suggested that electrically charged particles which move under acceleration produce alternate electric field and magnetic field. You can see the diagram over here. The electric component and the magnetic component to the direction of propagation, they are perpendicular to each other. Wave nature of light, students, we consider some wave characteristics. For example, wave nature of light, wave characteristics include wavelength. Wavelength is nothing but the distance between two crests or two troughs or 2 points in a wave. Next, we have frequency. Frequency is nothing but the number of waves per second. Time period is the time taken for the completion of one wave. Wave number is the number of waves per unit length. Amplitude is the maximum displacement from mean position, and wave velocity, speed of light that we take, which is 3 into 10 raised to 8 meters per second. We are considering electromagnetic radiation over here, which is frequency times wavelength. Next, students, this is the electromagnetic spectrum. So we start from cosmic rays, gamma rays, X-rays, UV, infrared. Between UV and infrared, we have the visible spectrum. Students, you should remember this. The visible spectrum goes from 400 nanometers to 750 nanometers, and then we have microwaves, radio waves, and long range radio waves. This entirety is the electromagnetic spectrum, and this is Vibgyor. Okay, I hope everyone knows that. Next, students, we have the particle nature of light, or we also call it as the Planck's quantum theory. Now, students, wave nature of light could explain concepts like diffraction and interference, but it couldn't explain concepts like black body radiation, photoelectric effect, heat capacity as a function of temperature, and the line spectra, or the spectrum of the atoms. And hence, in order to explain this, Max Planck came up with a new theory, which is called as Max Planck's quantum theory. Now, for that, students, we have something called as black body radiation. What experiment was being done, students, is what we observe here is, as the intensity of light increases, the wavelength first increases at a fixed temperature, and then it again decreases. Now, if you increase the temperature, what we observe over here, students, if you increase the temperature, the peak intensity wavelength shifts behind. I repeat, when you increase the temperature, the peak intensity wavelength shifts behind. So over here, though T2 is greater than T1, the wavelength at maximum intensity, lambda 2, is less than lambda 1. And you can say the frequency nu2 is greater than nu1. Moving ahead, students, so what exactly further is Max Planck's quantum theory? Radiation, students, is not continuous. The energy here is discrete in the form of small bundle of particles called as quanta or photon. So you can consider light or radiation energy as small bundles of particles, which we call as quanta or photon. Energy of each quanta is given by the expression E is equal to h nu, where h stands for Planck's constant, nu is frequency. It is also given as E is equal to hc over lambda. Planck's constant h is given as 6.626 into 10 raised to minus 34 joules second. Hence, students, energy can only be these particular values: 0, h nu, 2 h nu, 3 h nu. There cannot be any value in between. It is something like this. When you climb a stair or you come downstairs, you can skip one, you can skip two, but you cannot stand anywhere in between the steps. Similarly, energy can take only these discrete values, not in between them. Moving ahead, students. Next, we have photoelectric effect. Henry Hertz was doing an experiment where on metals having low ionization enthalpy, when light was bombarded, electrons come out of these metal, and this was explained by Einstein using the Einstein's photoelectric equation, which says that the energy of the incident light, or the photon, the energy of the incident photon is used to perform work function phi, and some kinetic energy is given to the electrons which are coming out. The formula is given as the energy of the photon h nu, work function is h nu naught, where nu naught stands for threshold energy, threshold frequency. Now students, the incident light frequency nu has to be greater than nu naught for the electrons to come out of the surface. Second, what I want you to remember is the kinetic energy of the electrons which are coming out from the surface is a function of frequency, does not depend upon the intensity of the incident light, whereas photoelectric current depends upon the intensity of the incident light. Next students, we have spectrum. What exactly is spectrum? It is the phenomena of splitting of a beam of light into its constituent colors. There are two types of spectrum students. One is emission spectrum, one is absorption spectrum. As the name suggests, what you mean by emission spectrum is, let's say if you have a gas, heated gas, it will release some particular frequency, some particular wavelengths, that is called as emission spectrum. If you incident light on that gas, it will absorb some particular frequencies, particular wavelengths, that's called as absorption spectrum. Emission spectrum is further divided into two parts. One is continuous spectrum, the other one is discontinuous spectrum. Continuous spectrum students mean like a rainbow. Let's understand what is a discontinuous or line spectrum. Here we have the hydrogen spectrum. The wavelength students for hydrogen spectrum is given as 1 upon lambda RH into Z square, 1 upon N1 square minus 1 upon N2 square. Nu is wave number, lambda is wavelength, RH is called as Rydberg's constant, Z is the atomic number, and N1, N2 are where the transitions of the electrons are taking place. Depending on that, we have 5 different series: Lehman, Balmer, Paschke, Brackett, Hund and Humphrey, and the related data, and for which particular region do these wavelengths fall in. Also students, just remember that Balmer falls in the visible region. Whenever the transition is from 3 to 2, you get red color. The transition from 4 to 2 gives you a green color. Then blue color is 5 to 2 transition, and the 6 to 2 transition gives you a violet color. Next students, we have Bohr's atomic model. This came after Rutherford, and in Bohr's atomic model students, Bohr's atomic model is applicable only to hydrogen and hydrogen-like species. According to Bohr's atomic model, the force of attraction between the nucleus and the electron is balanced by the centrifugal force. The angular momentum of the electron in Bohr's model is quantized. MVR is equal to NH upon 2 pi. The next, we have very important formula students. This is the formula for radius of Bohr's orbit. I have given both the expressions. The first one is direct expression. Second expression students JEE Advanced में पूछ सकते हैं. Then we have the velocity of the electron का formula. Then we have the formula for total energy of the electron. Total energy of the electron students is given in terms of joules per atom and also given in terms of electron volt per atom. Some more expression students, the frequency of electrons in Bohr's orbit and time period is just the inverse of frequency. However students, there are even some limitations to Bohr's model. The limitations to Bohr's model is, see, Bohr's model considers only the particle nature of light. It did not consider the wave nature of light. Bohr couldn't explain certain phenomena which is called a Zeeman and Stark effect, which is the splitting of orbital in magnetic and electric field. Second students, Bohr could not explain the ability of atoms to form molecules. Because of these drawbacks, and there are two major drawbacks students, which we will study in the form of de Broglie's wavelength. which is the dual behavior of light. We need to consider the particle nature and wave nature of light. Now students, de Broglie says that matter like radiation has both particle as well as wave like nature, and de Broglie also gave the wavelength formula. And students, this is applicable only to subatomic particles, where de Broglie's wavelength lambda is equal to h upon p. P stands for momentum. It is also equal to h upon mv because momentum is mass times velocity. The same formula for de Broglie's wavelength in terms of kinetic energy, and the same formula, students, in terms of when a particle is accelerated through a potential difference of v. Depending upon which particle, I have written subsequent formula, students. This is the wavelength for electron, for proton, and for alpha particle. V is the potential difference which was applied. Next, students, we have Heisenberg's uncertainty principle. So the uncertainty principle says that it is not possible to simultaneously determine the exact position and the momentum of the electron. This was also a drawback in Bohr's model. Now, Heisenberg's uncertainty principle, students, rules out that there is a path or trajectory of an electron around the orbit. It was said that the electron is moving in spherical orbits, in circular orbits, in elliptical orbits, but they are not. This was proved by Heisenberg's uncertainty principle. I have written the uncertainty principles in different forms, students. This is the uncertainty principle in terms of position and in terms of momentum. This is in terms of position and in terms of velocity. This is in terms of energy and in terms of time. This is in terms of angular momentum, students. And this is, students, uncertainty in terms of wavelength. Make sure you note down all these important formulas. Finally, students, we have the quantum mechanical model of the atom. I have the Schrodinger's equation on the board, though they will not really ask Schrodinger's equation. But when we solve Schrodinger's equation, students, we get what are called as quantum numbers. Now, there are, students, after solving Schrodinger's equation, we got three quantum numbers, which is principal quantum number, azimuthal quantum number, which is also called a subsidiary quantum number, or orbital angular momentum quantum number. We have magnetic quantum number, and we have spin quantum number. I have also written their formulas. With the help of this, students, spin quantum number was later introduced. It was not, we did not get it from Schrodinger's equation. Next, students, we know that if principal quantum number is 1, angular orbital momentum quantum number or azimuthal quantum number can go from 0 to n minus 1. So we get the subsequent values. Magnetic quantum number goes from minus L to plus L, and spin quantum number. Now, students, principal quantum number gives me the energy of the electron. Azimuthal quantum number also gives me the energy, but also gives me where is the subshell to which the electron belongs. Subshell you see over here, SPDF, and the corresponding azimuthal quantum number for the same. Magnetic quantum number, students, gives me the orientation of the electron, and the spin quantum number gives me the spin of the electron. Next, students, we have the different shapes of the orbitals. The S subshell is spherical in shape, P subshell is dumbbell, and the D subshell, students, is a double dumbbell. Next, students, we also have a concept which is called as a node. What exactly is a node? Node is a region in space where the probability to find an electron is 0. Now, I have written, students, in red the corresponding nodes and the nodal plane. I've also written the formula for radial nodes. The formula for radial node is n minus L minus 1. For angle node is L, and total number of nodes is n minus 1. Next, students, I've written some specific formulas for you. These formulas will help you to directly get answers. You can quickly copy them. Finally, students, we have the filling of orbital Aufbau's principle, which helps us also write the electronic configuration. Make sure you remember this sequence. So the energy of the 2s orbital is less than 1s, 2p orbital is less than 2s. So it's like in increasing order. But students, this is for multi-electron system. For a uni-electron system, the energy order would be like 1s, then 2s energy will be equal to 2s, then 3s energy will be equal to 3p, which will be equal to 3d, and so on. So for hydrogen atom, this is the sequence, but for multi-electron species, the energy in increasing order is given here. You can also use the n plus L rule to find the energy, where you find the sum of the principal quantum number and azimuthal quantum number. Next, people, we have something called as Pauli's exclusion principle. Pauli's exclusion principle says that no two electron in an atom can have the same set of all four quantum numbers. What does that mean? Let's say I want to know the quantum numbers for the last two electrons of magnesium. So as in the principal quantum number is 3. Since it is s subshell, the azimuthal quantum number is 0. Magnetic quantum number is also 0. So the first three quantum numbers for both the atoms will remain the same. However, the spin quantum number will differ, and hence they will not have the same set of all four quantum numbers. Similarly, we have Hund's rule. Students, Hund's rule states that whenever we are filling electron in orbital, you will first fill one spin and then you start filling and pairing the electron. What that means is, let's say first a clockwise, then you have an anti-clockwise spin electron. 2s also has first clockwise, then anti-clockwise, and in 2p4, students, what will first happen is the same spin electrons will fill the orbitals first. So let's say if I take clockwise, 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 and then pairing of the electrons will take place. This is Hund's rule of maximum multiplicity. Next, students, we have the probability density curves. I have given the probability density curves with the probability density function versus the distance from the nucleus. I have given it for different orbitals. I have given for 1s, 2s, 3s, and I have written all the orbitals here. These graphs are very important. And finally, students, from the electronic configuration, I want you to remember that copper and chromium have half-filled electronic configuration because of half-filled shells are more stable. So students, this completes our quick run of atomic structure. I hope I helped you cover all the concepts. Make sure you use this to write all the formulas, make your own short notes, and if you want such videos, please let me know in your comments. Thank you so much, students, for watching the video.